the last video on the kinetic model, we used a numeric pulse as the excitation input to trigger our model, and setting the right parameters as we discussed, we could create a nice sound that when we looked at the scope created a traditional damped pattern that we'd expect from a spring being set into motion and then damped, in this case, through viscosity, fluid friction. But there's other ways we can trigger the kinetic model. Another simple one is to use W, our gate. Let's try that. We have a setting similar to before. I've set viscosity a little lower to make it a little more bell-like. Look at the fingerboard display up here, and I'll press and release quickly. When I press, I get one sound. When I lift, I get another sound. It's a double attack. What does it look like on our scope? You can see when I press the fingerboard, I gate an impulse into the model, and when I lift my finger, another impulse is created. Why is that? Let's try it a little slower. I'll press and get a sound. Let it decay. Now I'll release. Let's see what that looks like on our scope. Look what's happening. I seem to have a complementary waveform. When I press, I get one pattern, and when I release, I get what looks like an inverted pattern. So what could be going on here? Here I've extracted some waveforms. You can see when I gate on W, I go from 0 to 1, and I'll remain at 1 as long as my finger's pressed. When I do that, a waveform starts and then it decays even though I'm holding, because we do have viscosity turned on, so that will damp the waveform. Now when I release W, I will gate off, another waveform starts, and that decays through viscosity as well. Let's take a look at a blow up. What happens is I inject this quick positive force into the model. You can see the waveform starts in a certain direction. That waveform continues as we discussed. Then when I release, the waveform starts in the other direction. Well, that makes intuitive sense. If I'm pushing the model in one direction and I hold it and then I release, the spring will move in the other direction. So looking at our model as it's defined on the kinetic modeler. So if I have a mass on the spring and I gate it and I give it a quick positive force and hold it there, what happens is the mass moves up to a position where the force of the spring compensates for the force that you're applying, and then it starts oscillating around that position until it comes to a rest due to the damping. Now I'm holding it there, and so when I ungate and suddenly stop pushing, the spring brings that mass back to its resting position where it again oscillates until the damping stops it. Now we could have done the opposite. We could have gated it in the negative direction. Only to do that, I need to create a little formula. I have one here. Now instead of using W, I'm using a formula that gates W. Here I have the option of having this be a constant or gating it with a press on the fingerboard. I can set that to a negative value, and I should hear basically the same thing, only now when I press and release, it's like I'm pulling the spring down, holding it, and letting it go. And if I want to look at the trace, pattern's the opposite way around. Christoph also notes that when you're using a sound interface with a plug-in scope like this, those sound interfaces have a built-in DC cut, so you mostly don't see that DC offset. You just see a bit of it setting up at the beginning of each wave, and we can notice that in some of the waveforms that we see here. Up till now, we've just been using a pulse or gate, a very quick impulse to trigger the kinetic model. In both cases, it doesn't matter how long I keep my finger on the fingerboard to create the initial impulse. With W, as long as I hold it, I'll continue to apply the force, but the initial impulse is very quick in both cases. But what happens if we try and apply a smoother force to the kinetic model? Well, if you recall, when we started out, we took the interpolation down. Let's read a little bit about that. We'll consider persistence later. interpolation smooths changes in formula value. Unlike persistence, this affects both decreases and increases in formula value. If interpolation is off, 0, the formula values are not smoothed at all, stepwise evaluation, and in many cases noise or aliasing will result. Most commonly, the interpolation is set around 40 to give fast response without introducing stepping artifacts. If the interpolation is large, the formula changes slowly. Now I turned this off initially because we wanted to hear exactly what the kinetic model was doing without any other effects applied. Let's go back, look at our scope, play the tone. Our waveform was in the plus and minus 0.2 range on the scope. I don't care what that means right now. I'm just talking in terms of relative terms. What happens if I take interpolation up a bit? Let's take it up to about 25. We'll see how that might affect the amplitude of the waveform. You can see that amplitude is decreased. We still have a bit of that stepping DC offset artifact in there, but the overall amplitude has been decreased when I start smoothing the data input as force into my model. Let's smooth it even more. Let's go up to halfway about. I should see a relative decrease again. If I increase it all the way, I can only hear the faintest of tones, and I don't see anything on the scope at all. So what's going on here? Well, let's think about it. Originally, in my model, whether I'm using a pulse or using W gate, the initial input into the model is a very quick force. Think of hitting your finger with a hammer. But let's say I push that spring up slowly with my finger and let it down slowly. I'm not going to apply nearly as much force on my model as I did before as an impulse. The numeric input into the model from this smoothing function is going to decrease its amplitude. Let's turn on the show formula value, and you'll see at full interpolation value, that initial pulse that was so quick, I see a little bit of ramping up and down now. And if I use a formula for W instead, where I can see the value, if I gate and press now with full interpolation, look how long it takes for the value to go to its max. There, we finally got there. And when I release, things will smooth on the way down for interpolation. So that's something to be aware of. Actually, little interpolation might help for certain kinds of presets. For others, you may want, for the kinetic model, just that initial big burst. And that brings us to the use of Z, our pressure function, as the excitation input for the kinetic model. Now Z is an exponential function that goes from 0 to 1. We can create a formula that's the same thing to play around with. Let's do that so we can experiment more. We'll turn interpolation off, and I'll press as hard as I can and release, and we'll see what happens. You can see that we have a very low amplitude here. This is like before with W, where I have an on and an off component, so I can see two separate waveforms developing, but very low amplitude. I can bring this up to its max of 2. Let's see if that has any greater effect. Yeah, it does, because we've increased the force, so that makes sense. It's still very low in amplitude compared to what we would have if we triggered it with a gate or a pulse. So when we're dealing with Z as the impulse into the kinetic model, not only does it have a smoothing function as you press the fingerboard, you will also for some time have your finger held down, so like W, you'll have a force applied, and that mass will only be able to oscillate around that point, in effect limiting the size of your container. So it makes sense that Z will have that decreased amplitude versus W, which gives you that quick impulse. We can try a few other things here. The square root function goes to max a little sooner, so maybe that will create a bit more amplitude. Yes, it does. So you can see the kind of function you apply with Z is going to affect both the amplitude and the waveform to some degree. Now we're using continuous here. We can try a derivative function and see if that changes things any. It certainly does. So you can play around with Z for various shapes. You can even set Z to a stepping function. In this case, I can press partway down and the first step will trigger. As I continue pressing down, the second step will trigger. We'll offset the first a little bit since it won't play if I have it on its 0 setting. Here you can see as I pressed halfway down, I got the first step, and then as I continued pressing, the second step came in. And this one, because it moves in discrete steps, is closer to the gate function that we had before with W. So we covered the excitation of the kinetic model using a numeric pulse, using a pulse of noise, using a gate, using smoothing functions on the gate, and using Z, which in itself is a smoothing function, but has various options that you can set. Let's talk about the height parameter now. Height defines a mechanical limit due to the size limit of the spring, or the fact that it is moving in a limited area. If there is no bouncing, we'll talk about that with elasticity, the spring motion will quickly stop when reaching the limit. At this point, it will be stopped, losing all its kinetic energy. So height limit is very different from audio signal clipping. When height is set to 0, the spring only has a very tiny space inside which it can move. Intuitively, we can see that if we have our original container, which can support an amplitude of that mass moving from top to bottom, if we now limit the size of the container, that means the maximum amplitude I can achieve is obviously less. A secondary effect might be if I apply the same force that I did before on the object, I might hit the edge of the container where before I might not have if I was moving within the original container space. Let's demonstrate this in a simple way. I put a barrel on height, which I've defined in the matrix. That barrel will go to -1 as I increase it, to -1 because height is set to its maximum amount, so as I increase the value of the barrel, I will in effect be subtracting from that till I get to 0. I'll bring viscosity down to 0 to create a constant sine wave, and then I'll reduce the height of the container, and you can see what's happening. At a certain point, I'll also increase after I've decreased, and we'll see what happens there. See, the height of the container is decreasing, so is the amplitude. I'll get down to about here. Now I will expand the container again. Amplitude does not increase. Let's continue to decrease. The height of the container is now 0, so the waveform has got a very, very small space to operate in. I can expand it from here and just a little waveform will bleed through. But obviously at this point, I've, for all intents and purposes, silenced. And as you noticed, when I increased the container after decreasing it, the amplitude did not increase. That mass inside the container had been compressed and it would be at a certain energy level. If I increase the size of the container at that point, I'm not going to increase the amplitude unless I impose a new force on the model. Let's try using height in a meaningful way in a preset. If I use a single pulse and reduce the height, there's not much that I can do after that point. The amplitude will be reduced. But what if I use a continuous set of pulses? I continuously apply repeated force to the model. So no matter what height I've set, I have a new impulse, and that height should then be applied to whatever my new force is. That might be a better way to use height in a real preset. Well, let's take our preset that we used before, and we'll put it back on the noise input. And instead of using a fast pulse, I'm going to use a slow pulse, a once a second pulse. So as we saw before, at the beginning, I'm going to get a pretty big noise burst into the model. And then from that point, I should taper away in the damped effect that I expect and start with a noisy effect that goes to a bell-like effect. I'll turn down the output a bit because noise can create quite a loud burst. And now let's see what happens. Well, as we expected, I see this really noisy component up front where I'm injecting all this noise as force into the model. And then when the pulse dies away, the damping will then go as we expect, and we'll get that bell-like sound at the end. So let's take that approach and create a preset. I'll inject a noise as we just did, and now on frequency, I'll start with a base frequency of 0.11, and I'll put a shape generator on that, rather slow, 0.2, and I'll ramp that up to 0.5. So my frequency is going to be ramping up. It might not be exactly this, remember, based on our mass and our spring constant, but this will create a rising frequency that will feed the model. And then this burst I want to put as continuous, not single cycle. So once a second now, I'll be bursting noise into the model. My pitch will be again continuous, ramping up from 0.11 to 0.61. I could change this to a higher or lower value, of course, on W. And finally, I'm going to take the height component and I'll put a shape generator on that as well. I'll set the shape generator cycle to a frequency higher than what I'm using for my pitch ramp, and I'll use a Hahn shape which is unipolar, going from 0 to my max here, which I set to 0.5, but I'll offset that with 0.1 because I don't want to start at silence. I want to start at a little bit of sound and then I'll increase it up. So I've got 3 shape generators going at the same time, with height continuously changing, getting higher, getting smaller. For that to work, of course, I need height to start at 0. Right? So I'll start my container with no height. Actually, it'll start with 0.1, so it'll start with a little bit of height, as we said. And all these shape generators will be moving together. I'll trigger the output with a gate, 0.5, because I don't want to oversaturate myself with all the initial noise that might come out when the container is at its full height. And let's see what happens. As we expect, I get that noisy component followed by the bell-like component, and the amplitude of these is constantly changing because the height of my container is going up and down and up and down. And in some ways, using this technique, it almost approaches the same kind of a sound that we got when we changed the nonlinearity on the spring constant. Just one of a million things you can do with a kinetic model. Now finally, the kinetic model doesn't have to exist on its own. I can feed the output of the kinetic model into, say, a filter. I'll use a low-pass filter here, and I'll set a relatively high low-pass frequency. I'll give it a bit of bandwidth reduction, and instead of outputting the kinetic model directly, I'll output the filtered version of that. So here I'm on the first filter. I'll output that like I did before, and let's hear what goes on there. I can change the frequency on that filter to something lower, and you can hear the change. I can change the bandwidth of that filter, of course, to something a little lower. You get the idea. The kinetic model can work in conjunction with every other bank and every other facility in the EaganMatrix, which makes it extremely powerful. That's enough for this video. Next time, we'll take a look at the anchor position, elasticity, and padding parameters.